Okay, this video is on the size adjustment that we employ in the model. So we have our base size that we just went through of 7 million in revenue that comes up with a corporate tax after corporate tax equivalent of 14.52%. Now, if we know what the cost of capital is for a large company that can be publicly traded, then we would have 2 points, so we can interpolate between those 2 points. So what we did is we took the microcap ETF called IWC is the ticker. It's the microcap ETF, and with that ETF we ran it on the Fama-French model. Made a slight adjustment because the IWC's median market or median revenue is around 230 million. So we looked at the change in SMB for the IWM and the IWC and the Spider, and we made a slight adjustment to the SMB. It's a minimal adjustment, but we had to adjust for the fact that we're going for 100 million, not 230 million. So using those factors, which are all the same except for the SMBs, slightly higher, very small difference in cost of equity. We plug those factors into the model, including the current implied equity risk premium, using the factors returns for those factors, for the beta, which is the market factor, very similar to beta. If you want to know more about Fama-French, research it. It's a more accurate model, in our opinion, than the capital asset pricing model. It's definitely more accurate in empirical terms, and it's logically a better model. Okay, so if we plug in those factors, we get a cost of equity of 11.14%. The IWC, the components of the IWC have a slightly negative debt to capital ratio. So we just zeroed out debt. Going across means obviously the cost of capital is equal to the cost of equity. Bring that down, and now we're saying, okay, so we know the cost of equity, cost of capital for a $100 million company as if publicly traded. So we want to know the private company equivalent. So there we take the cost of staying public and the cost of going public. Cost of staying public annually is $750,000 from surveys for small publicly traded companies. The cost of going public about 4%. So the total discount to value for those two things is around 12.6%. So if you increase the cost of capital by 12.6%, that increases it by roughly 1.5%, and that gets you a total private company equivalent of 12.5%. So now that we have the large company and the small company, we can draw a line between the two and just interpolate as opposed to extrapolate, which is obviously much safer. So the question becomes, what is the shape of that line? We strongly believe that the shape of the line is not a line or a straight line, it's a curved line. Two reasons why. As you take large privately held companies and make them very small, the smaller they become, the more unsystematic risk. They have fewer products, fewer regions, and so forth. So the total risk, the total beta, is increasing exponentially with decreases in size, and obviously vice versa with increases. Also, the costs of going public, liquidity, and so forth, or the cost of liquidity is going to rise exponentially, and that's where we use that relationship to get to our curved line. So let's go there into the size adjustment. And what we do there is we say, okay, so you've got changes in the cost of capital given just changes in size. Well, that sounds like you can arbitrage that by just putting two companies together. Well, putting two companies together costs money. So what we did is we said, let's use the Lehman formula to estimate the cost of putting two companies together. It's a sliding scale. As the company gets larger, the Lehman formula charges less as a percentage of the company. So we use that relationship as our exponent to determine the cost of arbitraging between changes in cost of capital from size to size. So as size gets bigger, the change in the cost of capital becomes smaller so as to not allow arbitrage. So it becomes larger as size becomes smaller because the cost of arbitraging as a percent of value becomes larger as you become smaller. So what we did is we did a test just to see how close it was. So here is our model. And if you plug it in, 7 million is 14.52 on an after corporate tax equivalent. Change it to double 14 million. So if one company bought another company just like it and doubled its size, its cost of capital would be lower, down to 14.03. So here's that change here, 14.03 to 14.52, implying that the company decreases in value. The two companies apart are 5% less valuable than they are together, well within the Lehman formula of putting those two companies together. So the rate of change in our estimate with those two fixed points, even when we curve it, the highest rate of change is, of course, at that lowest point, but it still gives us a safety cushion on an implied arbitrage. So here's the rate of change, greater here, smaller here, and from here to, let's take this thing here, let's change this to black. What we do here though is we look at this rate of change that occurs here, just at the 7, right at our mark, and instead of letting that curve continue to increase, we take that same rate of change all the way to 0, like that, just to be conservative on the downside. And that is what goes in our model. So when you change size, that's what it's doing. It's saying, hey, we know what the cost of capital is for a very large publicly traded company. We convert that to a private company equivalent. And we know what the 7 million is by the regression data and solving for the Gordon model. So the difference can be extrapolated or interpolated, and that's what this is doing, interpolating between those two spots. And that's the size effect.